Let's take a look at some other clarifications. And let's start recording just in case something I say is useful later on. One of the things that we want to be careful about is, especially when careful with our language about, is when we're talking about linear transformations, because the only transformations that we're dealing with are linear transformations, and linear transformations can always be implemented with matrix multiplication. So if T maps Rn to Rm is a linear transformation, there is an m by n matrix A such that T of x is equal to A times x. So we're tying the linear transformation to a matrix multiplication. But we have to be careful when we're talking about a transformation versus what we're talking about a matrix. T is a linear transformation, A is a matrix. T does not have pivots because T is not a matrix. The standard matrix of T does have pivots. T does not have columns and rows because T is a transformation and not a matrix. But the matrix of T does have columns and rows. So we got to be careful when we're talking about the transformation or the matrix of the transformation. Now, there are some things that we talk about belong to the transformation that don't belong to the matrix. When we talk about a transformation can be injective or surjective, or both, or neither. They're not mutually exclusive. So, but it's the transformation that can be injective or surjective. The matrix A, we would not describe as injective or surjective because A is not a transformation. T is a transformation. Injective, that's one-to-one. Surjective, that's onto. Those are things that belong to the transformations. We could talk about the kernel of T. T is a transformation, so T has a kernel. But A is a matrix. A does not have a kernel, even though if you said the kernel of A, people would know what you're talking about. But A has a null space. The kernel of T is the set of solutions to T of x equals 0. The null space of A is the set of solutions to AX equals 0. But we wouldn't want to mix those two up. We wouldn't want to say the kernel of A or the null space of T, because T is not a T is a transformation and not a matrix, and A is a matrix, not a transformation. So the kernel of T is the solution set to T of x equals 0. And this will be the exact same set as the solutions to A times x equals 0. But one of these words, kernel, should be we should only apply to the transformation. The other word, null space, is what we should apply to the matrix. So we want to be careful with what words go with what objects. Like I said, if you said the kernel of this matrix, people would generally know what you're talking about. But that doesn't make it good practice. We say in English, because English is a mess, we say things like begging the question when we mean raising the question. So a lot of times you'll hear someone, that begs the question, and then they ask a question. It's like, well, that is not begging the question, that's raising the question. Just say that raises the question, then say your question. But because English just changes what things mean all the time, now we say begging the question when we mean raising the question. This is why, yeah, words have meaning, but the context matters. When did those words take place? Because that could change the meaning of the words. Makes it really annoying. That's why I like math. Math doesn't do that to you. So we could also talk about things like the range of T. So T, a transformation, has a range. That would be all the images under T. So the T is this is going to be a subspace of the codomain. That's going to be all the images under T. And it'll be a subspace of Rm, the codomain. But we wouldn't want to talk about the range of A because A is a matrix and not a transformation. However, we could talk about the column space of A, which is the set of all linear combinations of the columns of A, which is a subspace of Rm. We wouldn't want to refer to Rm as the codomain of A because domain and codomain are things that belong to the transformation, not the matrix. Also note here that I'm saying this is the set of linear combinations of the columns of A. Because when we're talking about linear combinations, we need to be talking about a set of vectors. The columns of A are a set of vectors. A is not a set of vectors. Even though if you said linear combination of A, people would know what you mean depending on the context. But you want to make sure that you distinguish between things like the column space of A, the columns of A, and the matrix A itself. One that kind of straddles the line would be the rank. We would say that the rank of A would be the number of pivots in A. And sometimes we'll refer to the rank of a transformation as the number of pivots in the standard or the matrix of the transformation. I'm not really a fan of that, but if I was in charge, we wouldn't say things like the rank of T. But I think that's a place where we're just kind of sliding down to the oblivion that is using English to describe what's going on in math. Any questions? So these are all things that go together. I could reframe. One useful exercise might be to reframe this problem, or not, this wasn't a problem, I didn't actually do anything here. But take this matrix and say, this is the matrix of a transformation. This transformation goes from R4 to R3. We can see that the matrix of the transformation does not have a pivot in every row. Therefore, the transformation is not surjective. The range of T is a two-dimensional subspace of R3. We can also say that the kernel of the transformation is a two-dimensional subspace of R4. Because the kernel sits in the domain and the range sits in the codomain. So those are some things that were words that go with transformations versus words that go with the matrix of the transformation. That's the most problematic of in the class. The matrix of T versus the matrix T. Right, let's pause the video here and see what other questions we might have.